Good morning. Well, good whatever time it is. We're going to talk about redox reactions. And this is going to be a little different than anything that we've talked about last year. So this one's kind of new. But it's not a super difficult concept yet. We're going to build on this as the year goes along. But for right now, it's fairly simple. You just got to remember a couple of things here. Oxidation reduction reactions, that's just a fancy way of saying that electrons are moving around in the reaction from one atom to a different one, okay? So sometimes we call these redox reactions. If you're cool, you'll refer to them as redox. So that's easier than saying oxidation reduction all the time. So if you hear me referring to it as a redox equation, I'm just being cool, that's all. Oxidation occurs when an atom or ion loses electrons, okay? And then a reduction occurs when an atom or ion gains electrons. And the way that you can remember that, really easy way that's always worked for me, is Leo goes Gur, okay? Lose electrons, oxidation, gain electrons, reduction. Leo goes Gur. So in class, I might say Gur to you quite a bit, or I might say Leo to you quite a bit, to help you remember which is which. Because you're going to get to a point where it sort of seems like it should be the opposite. If you just kind of think about this, a reduction seems like it should be losing electrons, right? It's getting reduced, it's losing. We tend to associate those two words, but actually a reduction is gaining electrons. Its charge is being reduced, is what's happening there. So sometimes it's just easier to remember the Leo goes Gur. That will always steer you in the right direction. Lose electrons, oxidation, gain electrons, reduction. Okay? There are very specific types of reactions that will do this. It's kind of a whole category of reactions in chemistry where an electron gets transferred from one atom to another. And oxidation cannot happen without reduction. The electron's not just going to leave an atom without having somewhere to go. Okay? So if oxidation is happening, then reduction is also happening. If one thing is losing an electron, something else is gaining it. So then a couple other terms here, oxidizing agent and reducing agent. Okay? So the oxidizing agent is the one that is taking electrons from something else. Okay? It's causing something to be oxidized. Remember oxidation, Leo, lose electrons, oxidation. Okay? So if something is losing electrons, then it must be there must be something else that's taking them. Okay? So the oxidizing agent is the thing that's causing something else to be oxidized. And that means it is causing something else to lose electrons by taking them away. Okay? In this picture back here, the oxidizing agent is this one. Okay? The one that's taking the electron from the other one. The reducing agent then is the opposite of that. It's a substance that's giving electrons. So it's the one that's causing something else to be reduced. Okay, so again, back in this example, this is the reducing agent, the one that is causing something to be reduced by giving it an electron. Okay, so you just have to remember here, they're sort of opposite. Okay, whatever's being reduced is the oxidizing agent. Whatever's being oxidized is the reducing agent. Okay, and usually it's pretty easy once you remember they're opposites like that. Okay. Now, the way that we figure out when we look at a chemical equation if something is being reduced or being oxidized or whether a redox reaction is happening, we're going to use this thing called oxidation number. Okay? Now, I want you to maybe write this somewhere in your notes because this is important. Oxidation number does not equal charge. Okay? They're not exactly the same thing. The oxidation number is a number that we assign to an element just to sort of decide what it's doing in this compound. Okay, it's different than an actual charge. Now, sometimes the oxidation number and the charge are the same, which makes it confusing. So if you have, Na1 plus, it has an oxidation number of 1 plus and a charge of 1 plus. But not the charge and the oxidation number aren't always the same, especially when we're talking about molecular compounds. When we talk about molecules, really they don't have an all-out charge on them because they're covalently bonded. And so saying that that's a charge, it doesn't really make sense, but it's an oxidation number, okay? All right. Oxidation number is also called oxidation state, by the way. I didn't emphasize that back here, but you might see this written either way, so just so you know those two different terms, they mean the same thing. Okay, so here's the rules for oxidation numbers, and I'm going to go over these quickly here, and then I'm going to show you the packet that you have, your reading packet for today, because that has a more detailed list that will help you in pretty much any situation you might encounter as far as coming up with oxidation numbers. So if you have an element in its elemental form, it has an oxidation number of 0. Okay, now that's going to be anything like copper in its elemental form, just as it is on the periodic table. That's going to have an oxidation number of 0. You could have something like H2. H2 is hydrogen's elemental form. It's diatomic. Okay, that's its typical form that you'd find it in nature. That's going to have an oxidation number of 0. Or something like S8. Okay, that's the most common form of sulfur you're going to find in nature. So that has an oxidation number of 0. Okay, anything in its elemental, most basic form. Let's see here. Okay, the oxidation number of a monatomic ion is the same as its charge, and what we're talking about there are things like Na1+. I think I already gave this as an example. Okay, this is the charge on the sodium, is a 1+ or +1. Okay, so its oxidation number is +1, same as its charge. Nonmetals tend to have negative oxidation numbers, just like they tend to have negative charges, but depending on what compound or ion they're in, sometimes the nonmetals can have positive oxidation numbers. Okay, now again, that's weird because the nonmetals are typically not going to have positive charges. You would never see Cl1+ or something like that. Okay, but you might see chlorine with a +1 or a +3 or +5 oxidation state. Okay. So here's some of the specific rules for the nonmetals. Oxygen almost always has an oxidation number of -2. Almost always. Okay. The one exception that you need to know about is the peroxide ion. Okay. Peroxide is O2, 2-. Okay. And as you can see there, there's 2 of those oxygens, each with a 2- charge. And so overall, that's going to be a 1- charge in each of the oxygens. So its oxidation number is also going to be -1 in a peroxide. Okay. Everywhere else, oxygen is going to have an oxidation number of -2. Now, there's one other exception to that, and that's when it's combined with the other thing on the periodic table that's more electronegative than it is, and that's if you have any sort of OF, oxygen fluorine compound, which can happen on occasion. Okay, in that case, oxygen would actually have a positive oxidation number. Now that's weird, okay, but it can happen. Hydrogen is -1 when it's bonded to a metal, okay, so for example, sodium hydride, NaH, something like that. Then it's going to be a -1. It's going to sort of act like the non-metal there. Now, more typically, we're used to it being bonded to a non-metal, like in an acid, so for example HCl, and when we have something like HCl, then it's going to be a +1 oxidation state, okay, which is probably more what we're used to. Alright, next rule, fluorine always has an oxidation number of -1, and that's because it's the most electronegative on the periodic table. It's always going to take electrons away from other things. It's always going to get reduced. Okay, gain electrons reduction, GER. Okay, remove this. Now the other halogens, when they get combined with oxygen in oxyanions, okay, then they can have positive oxidation numbers. Typically, they're going to be -1s, the other halogens, okay, but fluorine's the only one that's actually going to take electrons away from oxygen. Okay, oxygen will take electrons away from any of the other halogens, and so they're going to have positive oxidation numbers there. Sum of the oxidation numbers in a neutral compound is 0. So when we add up all the oxidation numbers in a neutral compound, they should be 0. So again, going back to the NaH example, just as an example here, sodium has a +1 oxidation state because it is an ion with a +1 charge. The hydrogen has a -1 because it's combined with a metal. +1, -1, they need to add up to 0 in a neutral compound, okay? Now, if you have a polyatomic ion, then the sum of the oxidation numbers is the charge on the ion. So, for example, SO4 2-, okay? Now, each of these oxygens, according to our rule here, is going to be a 2- oxidation state, okay? So each of these is a 2-, and there are 4 of them, okay? So that equals -8. So in order for the sulfur, or in order for this polyatomic ion overall to equal a 2-, then this sulfur would have to be a +6, okay? Hopefully that makes sense. So you've got a -8 coming from right here, okay? So this has to be a +6 so that when you add those together, you get a -2, okay? And again, you're going to wonder why we're talking about all this. It will make sense in a minute. Okay, so let's determine the oxidation state of sulfur in each of the following. Actually, I think I just did one of them. Before I do that, let's go over here for a minute and look at some of the rules, the way that they're written on this sheet. Let me see if there's anything I need to add here. Oxidation number of any element in its free state, 0. Okay, we talked about that. Alkali metals is always +1. Alkaline earth metals is always +2. Fluorine is always -1. Oxidation number of oxygen is almost always 2-. Excuse me, that's something in my throat. Peroxide, we talked about that example. Superperoxide, oxidation number of each oxygen is -1/2. Now that's very uncommon. Let's see, covalent compounds, hydrogen is always assigned with an oxidation number of 1+. When hydrogen combines with a metal like NaH, okay, metallic halides. Yeah, this is just a little more detail, but it's essentially saying the same thing that we've already said. All of the oxidation numbers are assigned so that the sum of the oxidation numbers equals the charge. Okay, so there's really nothing to add there, I guess. So now we've got this problem here. Determine the oxidation state of sulfur in each of the following. So we've got H2S, okay? So on A, now we're just determining the oxidation state of the sulfur, but sometimes we're going to have to determine other things in order to figure it out. In this compound, sulfur, when combined with a metal, which hydrogen is in the front of this compound, it's counting as a metal here, it's always going to have a 2- oxidation state. Okay, now, the other way you can remember this is that sulfur in this compound, this is an ionic, well, it's a molecular compound, but it's one that's going to completely dissociate when you put it in water because it's an acid. But basically the sulfur here is going to have a 2- charge, and each of the hydrogens will have a 1+, which means the oxidation state, or the oxidation number on the sulfur, is 2-. Okay? In the second example, we already talked about this. S8 is the elemental form of sulfur, so that's going to be an oxidation number of 0. SCl2. Okay, now, what we've got here is 2 nonmetals combined, and the chlorine is the more electronegative of the 2. And the way that we know that is because it's listed second in the compound, and also you can look at the periodic trends and you can tell. So that means the chlorine is going to be a -1, and there's 2 of those. Okay, so that's going to add up to a -2, which means that the sulfur here must have a +2 oxidation state. Now again, very strange, because sulfur would never have a +2 charge, but it has a +2 oxidation state. Okay. Letter D here, Na2SO3. Okay, now we got to think about the things that we know. Okay. We know that sulfur is going to have, or sorry, sodium is going to have a +1 charge because it's an alkali metal. times that by 2. That gives us a overall charge, or overall oxidation number of +2 from the sodiums. Each of the oxygens here is a 2 minus, and we multiply that by 3, and that gives us a -6. Okay, so +2 from the sodium and -6 from the oxygen, and overall this compound needs to be neutral. So that means that the sulfur must be a +4 in this one. Okay, and then the last one we already did, but let's do it again here. So 4 times 2 is -8. So we got a -8 coming from the oxygen. The sulfur must have a +6 oxidation state here in order to add up to the 2 minus charge on the polyatomic ion. Okay. Next, replacement reactions. We talked about these last year as single replacement, or I think they're calling them displacement reactions on here. Single replacement reactions, same basic thing. Okay, in this reaction, silver ions oxidize copper metal. And so what's happening here, this is the net ionic equation for this reaction. Okay, and what's essentially happening here is this copper is going to end up giving electrons away to the silver. Okay, and so the copper is being oxidized. It's losing electrons, right? Leo goes Ger, lose electrons, oxidation. Okay, and the way that I know the copper is losing electrons is not because it's, you know, there's nothing in the equation that's showing the direction the electrons are going, but this copper goes from a 0 oxidation state to a 2+ because of its charge, or a +2. Okay, and so if this goes from a 0 to a +2, or a 2+, the only way that can happen is if it's losing electrons. It's losing electrons, so that's oxidation. Okay, and then the silver here is going from a 1+ to a 0 oxidation state because it's going into its elemental form, and the only way for that to happen, for it to reduce charge, is to gain electrons. So this is being reduced. Okay? Alright, the reverse reaction will not occur. Okay? The copper will not take electrons away from the silver. That just doesn't happen. Okay? And the reason for that has to do with the activity series, which we'll get to in a minute. Okay? But let's just practice here writing the balanced molecular and net ionic equation for the reaction of aluminum with hydrobromic acid. So we've got aluminum plus HBr, and this is going to be a single replacement here. Okay, we've got one thing, and this is what I described as a cheaters type relationship last year. Okay, where one thing basically kicks something else out of the compound and takes its place. Okay, now when we write the net ionic equation, we're going to see this isn't really a cheaters thing that's going on here. It's actually really just, you know, two things that have been very unhappy for a long time, and another one comes in, and, you know, they find each other or something like that. It's really, it's actually more of a thief type thing, like where one thing is stealing something from another, electrons. Okay, so we'll get to that in a minute, but when you think about it in the molecular form, it makes sense to think about the cheater type thing. So what the aluminum is going to do here is it's going to replace the other positive ion, which is the hydrogen. Okay, you need to make sure that you don't try and put aluminum and hydrogen together. Those are both positive ions, and that wouldn't work very well. So the aluminum is going to replace the hydrogen here, and we're going to end up with AlBr3, because the aluminum is going to form a 3+ charge, bromine is a 1-, and the hydrogen gets kicked out, and it becomes H2 gas. Okay. Now this aluminum is a solid to begin with. This HBr, I'm going to assume, is an aqueous solution. Doesn't really say that, but it's talking about a net ionic equation, so I'm thinking this is done in aqueous solution. And the AlBr3, if you look up your rules, that's going to be aqueous as well. So this is a gas-forming reaction that's happening here. Now, if we think about everything that's happening, and we break everything apart, so we've got the aluminum, which is solid, plus the HBr. Now, HBr hydrobromic acid, that's one of the 7 strong acids on our list. You know that because you have memorized the 7 strong acids, okay? So that's going to be H plus Br minus, okay? And then on this side, actually I guess I probably should have balanced this thing first. Let's see here, we've got a, well, if I put a 3 here in front of this bromine, then I'm going to have an odd number of hydrogens on the left side, and that's not going to work out well for me, so I probably need to multiply this by 2 first, which gives me a 2 here, and then I need a 6 here, and then I need a 3 in front of the H2, and that should do it. Okay, so let's try and keep this thing balanced as we're writing the overall ionic equation here. So that's 6 H pluses, 6 Br minuses, 2 Al 3 pluses, and let's see, 6 Br minuses over here as well when that breaks apart, because there's 3 Br minuses that come off of that compound, and we have 2 of those compounds total, plus 3H2 gas, and that one stays together because that's a gas. So then we just cross out things that don't take part in the reaction, and that's the bromine here, okay? So then we end up with 2Al solid plus 6H plus going to 2Al 3 plus 3H2 gas. Okay, and there's our net ionic equation for that one. And so when we look at the net ionic equation, it looks a lot different than the overall molecular equation, and our whole cheaters thing doesn't really work anymore. What looks like is actually happening here is the hydrogen is actually stealing electrons from the aluminum. The aluminum is going from a 0 oxidation state to a 3 plus over here. Okay, so it must be losing electrons, which means it's getting oxidized. Okay, and then the hydrogen here is going from a 1 plus to a 0 because now it's in its elemental form. And so that is being reduced because it's gaining electrons, Grr. Okay, so again, this is more like a thief type thing once you actually see the net ionic and what's going on here. The hydrogen is stealing electrons from the aluminum. Okay. Alright, let me see if there's anything real quick that I want to add to that from the chemical equation handbook. By the way, in chapter 3 here, the reason I included this chapter 3 is because it's got more practice with determining oxidation numbers, so that's kind of useful. Single replacement reactions, and then it's got a general activity series for the metals and for the non-metals. We're going to talk about that in a second. Active metals replace less active metals. Okay, that's the way that works. And then it just gives some examples of how this happens. And then it gives you some practice on that. So really there's not a lot else there that needs to be added. Okay, I'm going to take a break here for a minute, and then we'll come back with the second part of the video.